Okay, it's my great pleasure today to introduce Claire Max. Claire Max received her PhD at Princeton University in the astrophysical sciences on her work on plasma physics of pulsars, after which she went as a postdoc to UC Berkeley. After that, she spent 30 years at the Lawrence Livermore National Lab, in which she had a number of various kinds of leadership positions, including being a founding director for one of the institutes there. And then, since 2001, she has been at UC Santa Cruz and at the UC observatories, where she first was the director of the Center for Adaptive Optics, which she will discuss today, and now is the director of the UC observatories. So she's been known for a number of areas of research, but most prominently for her pioneering work on adaptive optics, which she will discuss today, which is a technique that is very important for astrophysics that removes the blurring effect due to the turbulence in the atmosphere on our astronomical observations. And she's the co-inventor of this very specific technique called the laser guide star system that she will discuss today. She's received a number of awards for her work, and it will take too much time to list them all, but a few that are included are the Madison Medal by the Princeton University. She was elected to the National Academies, and most recently the Weber Award by the AAS for astronomical instrumentation. And she'll tell us today how adaptive optics can be used for peering into the centers of galaxies to understand the supermassive black holes and their centers.
Thank you very much. I had a great day, and I want to thank you guys for hosting me and inviting me. We'll see if I can do this with two fists here. So I want to first thank my collaborators who are my students and former students, colleagues at the Max Planck, the CAC and LIC adaptive optics teams, and the Livermore adaptive optics team, and my colleague Don Gavel and Shelley Wright at UC San Diego. So I'll be showing a bit of work that most of these different people helped out with. And so I thought I'd start with telling you what this is, adaptive optics and laser guide stars, and then how they use AO, adaptive optics, to study nearby gas-rich galaxy mergers. So you have two galaxies which have lots of gas in them. They each have a black hole in them, supermassive black hole. And the question is, what happens to the nuclei and the black holes when the galaxies merge together? One of the things that happens to these galaxies when they merge is that they eject lots of material into the intergalactic medium, and I'll talk a little bit about a study that have started to study these outflows. And then I'll end up with a few extra slides that describe the use of adaptive optics for imaging the living human retina. So it used to be that if you wanted to study the function of the photodetector cells in the retina, the rods and the cones, you had to wait till whoever it was died and pull out their eye and preserve it and then look at it under a microscope. And thanks to the work that we've done at the Center for Adaptive Optics with our vision science and ophthalmology colleagues, they have been able to apply this to imaging the living human retina and be able to find out how vision works cell by cell in the eye. Okay, so introduction to adaptive optics. Here's a star, here's some turbulence in the atmosphere, here's a telescope, and this is what happens to the image of the star after it passes through the turbulence. So turbulence is what limits the spatial resolution of telescopes on the ground. You all know that turbulence is why stars twinkle, but much more important for astronomy, it spreads out the light, which should be more or less of a point source, a perfect diffraction limited image, and makes it a fuzzy blob. And fuzzy blob is a technical term, you know. So even ground-based telescopes, the largest of which today are 8 or 10 meters in diameter, have no better spatial resolution than a little 20-centimeter backyard telescope that you may have looked through when you were a teenager. And this is very pathetic, and we're trying to fix that. That's what adaptive optics is doing.
They do collect more light.
They do collect more light. Thank goodness. So if you haven't looked through an astronomical telescope, this is an amateur telescope imaging craters on the moon, and this is what it looks like. It's changing with time because of turbulence in the air, and that's what we're fighting against. So to put this slightly more quantitatively, if a star is sufficiently far away that it should look like a point, it's basically at an infinite distance from the point of view of being able to resolve any structure within the star. But instead of looking like a point, if you take a long exposure image of the star, it's about 1 second of arc across, which is much bigger than it should be. And if instead of taking a long exposure, you take a very short exposure that's so short that the turbulence of the atmosphere hasn't changed, it doesn't look at all like this. It looks like a bunch of individual dots or speckles. It turns out each one of these dots is at the perfect diffraction limit of the telescope, but if you took another picture a millisecond or two later, you'd see a whole different bunch of dots and a whole different bunch of positions. And by the time you add them up by some sort of central limit theorem, they look more or less round, adding up over many different incarnations.
Is that filtering out everything but a single wavelength, or is that over all wavelengths?
This is,
Range of wavelengths.
it's a range of wavelengths, but not particularly wide. And what we do with adaptive optics is literally use mirrors to put these spots on top of each other and to make a much smaller image of the star. And this is not a particularly good one. You'll see much better ones later in the talk. So the speckles in the star happen because of optical distortions, in this case from the atmosphere, also partly from the telescope. No telescope is perfect either. And so this is a way to correct for optical distortions. And what it does is it enables you to image with the resolution of what's called the diffraction limit, which I'll talk about in a minute. But it says that the smallest angular distance that you can distinguish two point sources from each other is about the wavelength of light divided by the diameter of the telescope. So if we had no atmosphere, this is what the image size would be, or equivalently the separation of two adjacent images that you can barely tell from the other. And this spot is in fact at this diffraction limit for the wavelength that this image was taken. It's applicable in many contexts, not just astronomy. I'll talk at the end about vision, but we were chatting earlier today about how much it's useful for biological microscopy. It's used inside lasers to correct for thermal distortions inside lasers. Some areas of very high precision laser machining use adaptive optics to improve their stability and so forth.
So was it also used for LIGO? I mean, for that was very important to have a very precise laser beam.
Yeah, I don't know. I don't think LIGO uses adaptive optics. Somebody tell me if I'm wrong here. Anybody know? Okay. So to go into a little bit more detail about the diffraction limit, so this is two different telescopes. One is small, the other is big. And notionally, since the best image you can get, the smallest image you can get of a star is roughly the wavelength divided by the diameter, a small aperture should produce a larger image of a star, and a larger aperture should produce a smaller image of a star. And this is what we're aiming for, is to get into this regime where we have diffraction limited images. So why does the atmosphere mess things up? I'm going to imagine now that we're sending light in from the left here, and these are surfaces of constant phase. For plane waves, they actually should imagine them extending out of the board. So here's my demo. Here's a surface of constant phase coming out of the board. And at the top of the atmosphere, this light has gone through thousands or millions of parsecs of intergalactic and interstellar space, and it's virtually a perfect plane wave. And then it gets to the last 50 kilometers of the atmosphere, and it gets totally screwed up, to put it bluntly. And that's because there are index of refraction variations in the atmosphere, and they change the direction of the light rays over and over again. It's not just two, it's many, many in the depth of the atmosphere. And so instead of a plane wave with parallel rays, you end up with a distorted wavefront. And of course, we all learned that the rays of propagation direction is perpendicular to the surface of constant phase. So now these rays are not parallel. Each one is going in a different direction. So that's the distorted wavefront. And so if you have a lens, say, or a telescope, it was built to focus parallel light rays onto a point limited by this so-called diffraction limit. But if the rays aren't going in the same direction, and worse yet, they're going in different directions at different places along the lens, this ray will be focused here, this ray will be focused here, this ray will be focused here, and you'll get a much blurrier image. And that's the heart of the problem. So just to show you how bad this is, this, believe it or not, is an image of a star, one star, greatly magnified and greatly slowed down. And you can see the speckles. There are all these different regions here that are each one a speckle. And furthermore, the centroid of the image, if you watch it wander, it's moving around too on the sky. So we have to correct both of those things. So this is the cartoon approximation of how to do that. Let's say you have a favorite galaxy and you want to measure something about the favorite galaxy, an image or a spectrum of that galaxy. And you're lucky you have a bright star nearby that's bright enough to let you measure the turbulence. So by some unspecified means so far, you have a fast detector and 500 times a second or 1,000 times a second, you use the light from that bright star to measure the turbulence. And then you use a computer to calculate the shape that you want to apply to a special mirror behind the telescope. Here's the telescope. Here's the mirror behind the telescope. So the telescope is big. The mirror can be this big or this big, much smaller mirror, with certain exceptions that I'll tell you about in a minute. And you put the shape on this mirror that exactly cancels out the distortions that you measure over here. So light from both the star and from your favorite galaxy then bounce off of this deformed mirror, and they are both cleaned up and made into roughly plane waves. And they can go into your science detector or your spectrograph or whatever.
So you're using the star to change the mirror.
Yes.
And then the purpose is to see the galaxy.
Yes. Yes. Imaging regular garden variety stars is boring. They're just dots. Big red giant stars and other supergiant stars can be exciting, but.
In principle, one could just do it in software.
Yes. In principle, let me go back here. One could take 500 of these images a second and process them together and figure out a way to put that data together to make this. And if we had perfect detectors with no noise every time you read out, that would be a perfectly reasonable way to go. It needs high computer power too, but you can do it. And that's called speckle imaging, and we've done that. But here's the problem. The detector that you have on the back end has a certain amount of what's so-called readout noise from the preamp, basically, every time you read the detector out. So if you read it out 500 times a second, you get hit by 500 times more noise than you would if you read it out once a second or once every 15 minutes. And then that noise makes it much harder to do the computational reconstruction.
Does that noise go away if you have a high-intensity source like the moon or the sun?
Yeah, it certainly gets better.
So you can do a lot more of this
Yeah.
software instead of expensive.
Yeah, in fact, the solar physicists or solar astronomers, whichever you prefer to call them, have solar telescopes. Almost all of them run adaptive optics 90% of the time. And after they run the adaptive optics, they do this numerical processing that we're talking about. So they do both to get the last little bit cleaned up. It's a perfectly reasonable idea. The sun is bright.
But you're saying there's some sort of quasi-analog way
Yeah.
that the light from the star can be more effectively, you can do it more effectively by deforming the mirror. It seems
Yes,
like
because you put all the light in one place. You take all this light and you put it in one place, and you measure the residual wavefront errors after you've already done the correction. So you have much higher signal to noise, to put it quantitatively. I'll show you that in a second. So moving ahead here. Slightly more rigorously, now we have the telescope way up here, the star is far away, and the light from the telescope is distorted, as we said. Behind the telescope usually is your adaptive mirror or your deformable mirror. And so you distort this so as to, mostly the best you possibly can, clean up this distorted wavefront. And so coming off this mirror are plane waves pretty much, except they're not perfect, but they're much better than they started out being. So you send most of the light into your high-resolution camera or your spectrograph to get detailed information about the object you're looking at. And a little bit of the light you break off and send into the device called the wavefront sensor that does these measurements 500 times or 1,000 times a second. And it goes through a control system, meaning a computer, that figures out how to translate these measurements into actual voltages that you apply to the actuators on the back of this mirror to change its shape. And let's see, I think this is called a closed loop feedback system or control system because you're doing the measurement after the light has already gone off the mirror that was corrected at the previous time step. So you can imagine a series of time steps. You do a measurement, you send a signal to the mirror, it has a certain shape. The next time step, the atmosphere has changed a little bit. But that light goes off the pre-distorted mirror, and so it's pretty close to being corrected already. And then you tweak it up by correcting it again. So it's called a null-seeking control system from that point of view. Yes?
So you're doing that with the guide star?
Yes.
Something that you assume is a point?
Yes.
Okay. But that's not what you want to look at. You want to look at it.
I'll get there. Ask me again in 7 or 8 slides. Okay. So, and it's important to say that the AO system fixes the image after it's bounced off the primary mirror of the telescope. When I give talks like this, because it's a sufficiently hard concept to grasp, some people think that we're wiggling this whole 10-meter mirror, the primary mirror of the telescope, and it's just too heavy. You can't move it fast enough. It has too much inertia and so forth. So you have to wiggle something else that's smaller. Okay, so this is the same image you saw before, the image of a star. Now this is on a different color scale. This is the improved image with adaptive optics. So now what used to be on several hundred pixels is on 1, 2, 3, 4, 6 pixels maybe. So you've taken all the energy in this and put them on just a few pixels. So this is actually, in fact, much brighter than the same color represented here. It's just that I've scaled each one so the brightest pixel in this image is white and the brightest pixel in that image is white. It's not perfectly corrected. You see this little halo around it, but it's a lot better than it was. And it's also stabilized. This is not jumping around on the sky very much anymore. So if I look at that same data, here's the image from the previous slide, and I plot intensity versus X and Y on the sky now. Instead of using color maps, I'm showing actual intensity. You've gathered, again, all of the energy that was in these hundreds and hundreds of pixels and put them in just a few. And so the peak intensity goes way up, and the size of the image goes way down. And if you imagine now that you wanted to image a planet, a faint planet around a nearby star. If it was without adaptive optics, you couldn't tell whether this is the planet or that's the planet or the planet is some other thing here. But by putting these all on just a couple of pixels, now if there was a planet here, you would be able to clearly see it. So contrast goes way up when you do this kind of imaging. Yes?
What's just the correlation with the atmosphere?
It depends on a lot of things, but typically 10 or 15 milliseconds, might be 5 milliseconds for infrared light, for example.
Thermal fluids or something?
No, it's due to, now I get to do my demonstration. Okay, good. So here's the plane wave that came from infinity at the top of the atmosphere. And what the atmosphere does to it is this. So it's not a plane wave anymore, it's all bumpy. And these are optical path differences. So you can almost think of this geometrically, because the light that reaches one of these peaks has gone through less optical path than the light that reaches the valleys. And what you do with your deformable mirror, by the way, is you reverse that. So you make the light that got there first travel farther, and they all catch up with each other. So why am I showing you this? So this is the turbulence, say, at one end of a 10-meter telescope, one edge. If I measure it at that edge, and I have a good way of knowing what the wind is doing, I can actually predict what the turbulence is going to be by the time it reaches the other side of the telescope. And that's the kind of thing that's just being done now. It hasn't been done until now on a production basis. I don't know if that answered your question. Sort of. Mostly it's the wind. It turns out that the time scales for changing the crinkles are much longer than the time scale for the wind to blow over the telescope.
When you, in the control system, adjust it to make this kind of inverse of the fixes it, you're able to somehow see what the phase is, and you know exactly what to do to that like little actuator, or is it just purely a feedback system that's trying to make it be a small
So what you measure with most wavefront sensors is the local tangent to the phase. You measure wavefront tilts, slopes. And if you wanted, it would be easy to integrate those slopes to get a wavefront, the full phase. In fact, you don't bother because that takes too long. So you just have an algorithm that makes the phase into voltages to send to the back of the deformable mirror.
But it is really like once you see those phases, you know what to do.
Yep.
It's not like
Yep. Okay. So here are some images all taken in the near infrared at a wavelength of 1.6 microns. And it's comparing no AO on a 10-meter telescope, no adaptive optics, Hubble Space Telescope, which is a 2.4-meter telescope, and adaptive optics on a 10-meter telescope for the planet Neptune. And it turns out that in this wavelength range, there's a lot of methane absorption in the atmosphere, which produces the dark regions, and the light regions are from clouds relatively high in the atmosphere. So without any adaptive optics, there's your canonical fuzzy blob. The Hubble Space Telescope NICMOS camera, which now is defunct, but this was the image that I found at the time, shows a lot more detail than this. But this is only a 2.4-meter telescope, and in principle, a 10-meter telescope should have 4 times better angular resolution, and that's approximately what it has at the same wavelength. So if we were to try and do this at visible wavelengths, Hubble can also image, say, at half a micron. We can't do that yet with adaptive optics. But we can do it very well in near infrared, and new systems are going down into what we'd call the red part of the optical wavelength range. So
why is the Hubble not seeing the upper part of Neptune? Because the atmosphere is not doing it. There's no atmosphere to do it.
this is methane absorption, so the light just isn't getting out. So the light from the...
What's absorbing the methane?
I'm sorry?
What's absorbing the methane in the Hubble?
Neptune's atmosphere?
Oh, Neptune's atmosphere.
Yeah.
Okay.
Sorry, didn't make that clear. What was I going to say? There are 2 telescopes that are run by the Air Force that are 3.7-meter telescopes that do image in the optical. They use it for imaging satellites and stuff like that. We'd like to be able to do that kind of thing on the really big telescopes. Yes?
On the wavefront or on the surface of this active mirror, how many active elements or pixels is involved?
So it depends on the size of the telescope and on what wavelength you're observing at. The one at Keck now has 250 active actuators, 250. The one that we have at Lick, which is going to shorter wavelengths, is about 1,000 active actuators. The ones that are planned for the next generation of big telescopes, which will be 20 to 40 meters in diameter, have something on the order of 5,000 active actuators. So okay. I can explain why later.
They are independent telescopes.
Independent actuators, that's right.
Of course, we were comparing to the Hubble telescope. Of course, the Hubble telescope nothing goes through the atmosphere, so there might be wavelengths that you just can't see.
Exactly.
Right?
Yeah, yeah. Ultraviolet light, far infrared light, precisely. Oops, I keep going back to my computer and I don't have to. So for the past decade, we've been in this situation where adaptive optics on large ground-based telescopes actually gives better resolution than Hubble, but just because they're bigger. But the field of view is much larger for Hubble than it is for adaptive optics because the turbulence tends to change if you look at different places in the sky. And it turns out that it has to be within sort of half an arc minute. Your guide star has to be within roughly half an arc minute of your favorite galaxy in order to really get a good measurement at the position of your favorite galaxy. Hubble can just do this anywhere in the sky, and so it has a much wider field of view. And one of the other directions, in addition to going to shorter wavelengths in the coming decade, and in fact starting now, is we're making adaptive optic systems that can go to wider fields, not as wide as Hubble, but much wider than they have been so far. So that's just for future.
Multiple simultaneous guide stars, or is there another technique involved?
Multiple guide stars and multiple deformable mirrors. So the idea is that if you can measure the different layers of turbulence in the atmosphere and make each deformable mirror conjugate to that layer, then you can broaden out the field of view. Okay, but so here's another example of this: Hubble in the visible and Keck adaptive optics in the near infrared, doing roughly comparable. And so why is that? Because Hubble is 4 times smaller, but the wavelength is 4 times shorter, and so we're basically lambda over d is about the same. So there's been a huge amount of science making use of this synergy, that if you look at the same object in the infrared with big ground-based telescopes and in the visible with Hubble, you put all that data together and you can learn a lot more about the physical conditions in whatever it is you're looking at. Okay, so this is just a little bit about how a deformable mirror works. This is the 0th order approximation. Here's your deformable mirror, here's your wavefront, and the 0th order approximation is that this part of the wavefront here and here has been delayed relative to this little notch. So the notch got ahead. So what do? You make a notch that's half as deep in the deformable mirror, and you send the light in and out, and by the time it's gone both directions, the back has caught up with the front because you made this part travel farther. So that's the whole thing. It's about optical path difference. And of course, we don't have notches. We have wiggly mirrors, but it's exactly the same principle. You make the part that's in front travel farther. Let me go back to this. This is a cartoon of the first kind of deformable mirror that was used, and that's still in use in many places. It's a very thin sheet of glass, and you glue actuators to the back, and you have wires from each actuator going to your computer. And you send voltages to the actuators, and they get longer and shorter depending on what voltage you send to the back. So those of you who work in the lab should already be worried because I mentioned the word glue. And anybody who's worked with glue knows it doesn't do the same thing every time. And so people are trying to get away from this technology, but it's worked well. And it's hard to scale to really, really, really big systems, because if something goes wrong with the glue in your 5,743rd actuator and you can't get to it, how do you fix it? But aside from that, it's fine. Okay. So there are a lot of different kinds of deformable mirrors. This is the kind I showed you. This one has 1,000 actuators. And it doesn't have a shiny coating on it, so you can look through the glass and see the actuators through the glass. Of course, when you use it, you'll make a reflective coating. You can do the same thing with 1,000 actuators in less than a centimeter using what's called microelectromechanical systems. These are mirrors that are made by the same kind of photolithography that your computer chips are made with. And they're about a factor of 10 cheaper than these. And you can mass produce them as opposed to these, which is quite hard to mass produce. This is about 1 foot across. This is about 0.5 centimeter across. A new kind of adaptive mirror that we're all very interested in is called an adaptive secondary mirror. So I'm going to back up and say how most astronomical telescopes work today. Is the light comes in from the sky, it goes off the big mirror and bounces up to a secondary mirror up here, and then through a hole in the secondary mirror to the instrumentation back here. And so what this does is it replaces this piece of glass, rigid piece of glass, with an adaptive mirror that itself can change its shape. So you're not adding any more optical components than you started with, and you are gaining control of the wavefront. And you can see this one hasn't had its reflective coating put on yet, and it's also upside down. Of course, it points downward. But now there are these mirrors at several telescopes, and a new one is being engineered for the prime European telescope called the VLT, Very Large Telescope in Chile. So, as people have pointed out, you need a bright star that's bright enough to do these measurements, and it has to be close enough to your favorite galaxy that the light from each of them goes through the same turbulence. And if it doesn't, you're in some trouble, because you can measure this star till the cows come home and you're not going to know what the turbulence was in the direction of your galaxy. And if you actually do the numbers, it turns out that less than 5% of the objects like galaxies in the sky have a bright enough star nearby. So this is just a question of how many stars are there in the sky of a certain brightness. You do the distribution function, you ask how many per square arc minute, and there aren't enough. So I'm moving over to the discussion of laser guide stars, because natural guide stars just aren't sufficient in many cases. Of course, if you want to look for planets around this star, you're looking at, by definition, you're looking at relatively nearby stars, so you can see their planets. And so those stars tend to be bright, and you're just fine using the star itself, because that's what you're interested in. So it turns out you can make your own artificial star using a laser, and this is what we suggested in the early 80s, a particular scheme for doing that. You tune a laser to that yellow light of the sodium D2 resonance transition. It's a ground state transition. The cross-section is very high. Well, why would you want to do that? It turns out that at an altitude of about 90 kilometers in the atmosphere, there's a naturally occurring layer of sodium atoms, neutral sodium atoms. And they're due to micrometeorites burning up in the atmosphere. So the meteorite comes in, it's going very fast. At about this altitude, the heat from friction in the atmosphere ablates away the atoms, and it turns into gas. And we go, oh, here we go, we're going to shine our laser on it and take advantage of that. So,
how bright is the laser you shoot up into the sky?
It's sort of 8th or 9th magnitude, if that's any help.
No, how many watts?
How many watts? 10 to 20.
So what about airplanes?
Yeah, what about airplanes? We used to have people standing around the dome with kill switches, and when they saw an airplane, they hit the kill switch. And so now it's all done with transponders. So aircraft have transponders. You have a system, little, basically phased array radar that makes the transponders respond, and then you know where your airplanes are, and it turns off the laser. You might also ask about spacecraft. It's not good form to shine a laser into somebody's optical system in a spacecraft and blind it. It doesn't go over well with the State Department. And so we actually coordinate with the US Space Command, and they tell us if you're pointing in this direction of the sky, you have to turn off your laser between 3:29 a.m. and 3:30 a.m. because there's some spacecraft going by.
I'm sure they also have a lot of fakes in there too, because otherwise they would tell you where all their spacecraft are.
Yeah, oh, don't get me going on this. You can go online and find out where all the spacecraft are. So, but we have to go through the Air Force because we live in the US. People who have telescopes elsewhere don't bother. They go online and make sure that they're not going to hit a spacecraft. And you can calculate the a priori probability of hitting a spacecraft. It's 10 to the minus 10, I think, per night or per year, one or the other. Okay, so we first started this at Lawrence Livermore National Lab. We had back here a building that contained a lot of copper vapor lasers that which are green light that pumped a lot of giant dye lasers, which will make any color light you want, as long as you send a seed beam in that's that color. And this laser light was actually sent underground to a building over here where they were experimenting with ways to separate the isotopes of uranium for civilian nuclear power fuel. It was called laser isotope separation. And it was rendered uneconomical because after the Soviet Union broke up, they made all of their separated uranium available on the open market, so much for that. So the price went way down. But anyway, we used their laser. We put a turning mirror underground and shined it up into the sky with a nice little half-meter telescope, and we had another telescope here to look at the laser spot. And this was an interesting endeavor, one of the more interesting ones in my life. There was we were advised by the public relations department at our laboratory that we should notify the community when we're going to shine this laser up because you could see it from a long distance away. We didn't want people panicking and so forth. So we did. And the community was quite interested and receptive. We explained why we were doing it, except for one lady in Pleasanton who lived about 10 miles away. And every time this laser went on, she would call the police, everything from her local police to the state police, the county police, and she would say, there's a UFO hovering over Livermore, sucking up its secrets through the laser beam. So that got to be kind of interesting. The policeman that we worked with was not pleased with this, but it was amusing. Higher than, yeah. There was also a freeway kind of over here, and we didn't want people stopping on the freeway, so we got the highway patrol involved. Anyway, that was fun. We graduated to Lick Observatory, and now we're doing this at Keck Observatory. And there are now 4. There are 4 lasers at the summit of Mauna Kea volcano functioning on a routine basis. And it's gone a long way since we had that little half-meter telescope in our backyard practically doing the experiments that showed that this would work. Okay. Can I get us to advance? Yes.
So am I right that it's just what you lit up in the upper atmosphere that's acting as this false start, that your optics aren't sensitive to the big bright things in its line?
No, it turns out that it's spatially separated because you're looking at a little bit of an angle, and so you can actually, it's physically alone up there, and then below it you see this big shaft of light. Okay, so I'm going to talk about using adaptive optics to study black holes in merging galaxies, and I'll digress on gravitational waves because I can't help it, and I might skip this part since I see it's already a quarter of. This is what the Keck telescopes look like on Mauna Kea, which is where these observations were done. This is what the laser guide star looks like. This is the bottom of the telescope here. The telescope itself is up there. And here are some Hubble Space Telescope images of nearby galaxy mergers. So if you look at computer simulations of galaxies in the evolving universe and ask about the merger histories of individual galaxies, galaxies are always merging with small satellites and small other galaxies. And every once in a while, you get a major merger, which is what we're looking at, of galaxies with equal mass crashing into each other. And typically, you see these great big tidal tails, and quite a mess is formed. This became interesting about 10 years ago because there were some computer simulations asking what was the relation between galaxy mergers and black holes lighting up and kicking out all the gas in the galaxy. And the scheme was, during one of these major mergers, the gas is stirred up. It has non-axial symmetry. It can have torques on it that allow it to accrete onto the black hole that we know is in the center of all galaxies, all big galaxies. And that black hole then emits a lot of radiation, X-rays, gamma rays, ultraviolet light, which ultimately push out the gas in the surrounding galaxy and leave you with what's called a quasar, which is basically a naked, radiating, accreting black hole. So we got interested in this. With this scenario, it's turned out that it's much more interesting from several other points of view But this is still one of them, and we want to know, what observational signatures do we see of this kind of thing happening or not. And so we started with gas-rich galaxies. These are galaxies that are almost but not quite merged together. And they still have two separate nuclei, but their nuclei are within 1,000 parsecs of each other. So they're very strong emitters of infrared light because they have a lot of gas. And there's strong star formation going on, and they're called colloquially ultra-luminous infrared galaxies, which are called ULIRGs for short. So that's the sample, and we're observing them at KEC. And so this is one of them. It's called NGC 6240. This is a Hubble image. Here are these big tidal tails coming out. In here, I'll show you there are actually two nuclei. This is relatively nearby, so we can see it clearly. And I'll show you where these tidal tails come from in the next image, I hope. This might not work. It's not going to work. It's a movie. Never mind. It was to show you that tidal tails get pulled out when two galaxies go by each other. So here's what Hubble sees in visible light, roughly half a micron or so. Here's what Hubble sees in the very center of the nucleus at 2 microns. So here are the two nuclei. It turns out each one of these has a black hole because each of the two galaxies that crashed together had a black hole. And this is what we see at Keck at the same wavelength. So now you're seeing this effect that if you're able to correct a telescope to the diffraction limit, it should be a 4 times clearer image at the same wavelength because the telescope's 4 times bigger. And we also see lots of things that aren't seen in Hubble. These little dots here are newborn star clusters, each one of them several million solar masses in size, and they're 10 or 15 million years old, and we can use them to trace the history of the latest crash in the merger sequence.
So the physical scale is, you said, is
700 parsecs between here and here. Okay, so looking a little more carefully, one might ask, where are the two black holes? You might think that what you typically are looking for in infrared light is very hot dust from the region immediately around the black hole. And, so here's the north nucleus. Is that the black hole? Is that the black hole? Is that the black hole? South nucleus, no point sources at all. So where are they? And this is looking in more detail now, blowing up the two nuclei. Again, here are the 3 potential black holes, lots of other structure here. Again, there's no point source at all in this other nucleus. So we wanted to measure the mass of these black holes, but first we had to figure out where they were. So we cheated. We used some data that had come from long baseline interferometry in the radio wavelength. So black holes emit non-thermal radiation and radio waves. And radio interferometry can yield superb spatial resolution, and these two guys had actually measured the positions of these 2 point sources, which are the 2 black holes, at a wavelength of 5 gigahertz. And when you're measuring with radio, you pin your entire coordinate system to the coordinate system of all the known quasars on the sky. So it's a very, very good astrometric coordinate system. You know exactly where things are, absolutely. And we then lay those contours over our 2 images. And here's the north black hole. Where's the south black hole? We can't quite see it here. It turns out that if you look at a longer wavelength, which gets through the dust that's very heavy in this region, there's a point source right here. So here are the 2 black holes. And the next step was to try and measure their mass. And so how do we do that? Measuring black hole masses, you want to get close enough to the black hole that you're able to see matter that's influenced by the gravity of the black hole, not by the gravity of the galaxy. And it turns out that's at this special radius called the sphere of influence, this radius here, where you're equating the kinetic energy, sigma squared is the velocity dispersion, with the gravitational potential energy from the black hole. So sigma squared is from the galaxy. M black hole times G is the gravitational potential of the black hole, and it turns out that's roughly 1,000 parsecs for a 10 to the 9th solar mass black hole with a typical velocity dispersion. And we can spatially resolve that. We can resolve 50 parsecs, so we get something like 20 resolution elements across this gravitational sphere of influence, and we can actually measure the effects of the black hole. And we do that by spectroscopy. We have an imaging spectrograph where you can imagine this is an image, and at every pixel in the image there's a spectrum. And so we get a full spectrum at every pixel, and we measure the velocities using the Doppler shifts of spectral lines, because the shift in the wavelength divided by the original wavelength of a spectral line is the change in the velocity compared to c. So we can just measure the spectral shifts of these lines. And so here are some lines in our data. These happen to be CO absorption bandheads. Here's the template star. All of this structure is real. All these wiggles are real. And the asymmetry is real, so we can do a very good measurement of the wavelength position of these features. And I want to walk you by what we're looking at. If you have a black hole in the center, Kepler's laws give you this roughly hyperbolic behavior of velocity with position. So as you get closer and closer to the black hole, the velocity goes larger and larger. We see that in our solar system. Mercury goes around the sun much faster than we do. If you smooth over the fact that even a diffraction-limited telescope has a finite resolution, you don't see this part where the velocities go to infinity. You see something that has two peaks in it. And so here's what the ideal curve is. This is one cut through our data. Not quite as pretty, but this is a one-dimensional cut. It implies that the stars near the black hole are in a thin disk. I'll show you that in a minute. And the black hole mass is about 1 billion times the mass of the sun. Big black holes. And here's the actual data that we use, two-dimensional data. So the material here is going away from us. The material here is coming toward us. The region where there's this very steep gradient in velocity is where the black hole is. And here's a disk model that happens to be the best fit disk model, and we get something between 9 times 10 to the 8th and 2 times 10 to the 9th solar masses for this particular black hole. And the other one has roughly similar mass, within 50% or so. So then we can start asking more general questions. We've done this now for 15 or 20 galaxy mergers. And one of the things that is challenging to people who study galaxy evolution at the moment is referred to as the M-sigma relation, the mass of the black hole and its relation to the velocity dispersion of the bulge of the galaxy. And it turns out that if you look at many, many galaxies, and now there's much better, more tightly constrained versions of this graph, there's a pretty tight correlation between the black hole mass and the properties of the bulge of the galaxy. So one hypothesis is this is happening. So what happens to this scaling relation when galaxies merge? So do the black holes, which each galaxy brings to the party, grow at the same rate as the bulge velocity dispersion, so they would evolve right along the scaling relation if sigma and m are growing at the same time? Or does one component grow faster? So in the middle of a merger is the black hole growing in mass really fast, and then only later does the velocity dispersion catch up? Or is it the other way around, that the black hole mass doesn't grow very fast, and later the black hole mass catches up with the velocity dispersion? And we've actually done these measurements. And so here they are, at least for 9 galaxies. And what we find in this particular kind of galaxy is that the black hole masses grow first. And the implication is that later they'll end up on this general correlation function once the velocity dispersion of the bulge has a chance to virialize, once the separate nuclei actually homogenize into one vaguely spherical bulge. So this is interesting. We want to pursue it more, and it actually might have implications for how these scaling relations take place. So I'm getting very close to the end, and I'm going to, maybe I'll skip the part, no, I'm not going to skip the part about gravitational waves. So one question is, which supermassive black holes will merge eventually so that they might emit gravitational radiation? And this is called the last parsec problem. So if you do a simulation of two black holes with just stars in the center of the galaxy but no gas, it turns out that by the time the two black holes get within the roughly 1 parsec, 3 light years of each other, there's no further way for them to lose angular momentum, and they just keep going around and around forever. Some simulations like this one by Lucio and Meyer have shown that if there's a lot of gas in this region, there can be drag of the black holes against the gas, and they can lose angular momentum and spiral in. And so the question that we were interested in this class of galaxies is how much gas is there, and is there enough to do this? And what we find in our sample, in this case it's 17 galaxies, is these nuclear gas disks, radii a few hundred parsecs. Every single case has a disk dense with dust and gas, rotational velocities of a couple hundred kilometers a second, and in most cases they're vigorously forming stars. And so here are a rogues gallery. Blue means the material is coming toward us, red means it's going away from us. This is just meant to show you there are a lot of disks. And so I'll finish before I get to the eye with the last parsec problem. The two black holes can lose angular momentum by a dynamical friction with stars, and they move closer together. But the computer simulation suggests that by the time the black holes are separated by a parsec, they've actually kicked out all the rest of the stars that are left. So it's just those two black holes and no more stars. And can they find some way to lose angular momentum and merge in this context? And we think that our discovery of these disks actually might have something to say about that, because there's a dense reservoir of gas to feed into the central parsec. If it can get from the region at about 20 parsecs where we're seeing it, down into the 1 or 2 parsec region, then two things can happen. One is the black holes might lose angular momentum to the gas, which is what we were talking about before. And there's some interesting physics potentially in how this gas might form disks around either both or one of the black holes. But also this disk is making stars like crazy. And if some of these stars get scattered back into the lost cone where the black holes are located, they can actually provide more stars for the black holes to lose angular momentum against. And most of you know that gravitational waves have been seen from stellar mass black hole mergers. So today this was from a slide that I enthusiastically put together the day after the LIGO discovery, but here's a measurement of time going this way and the strain, the distance between 2 points in the vertical direction, and these are taken from 2 different locations, one in Washington, one in Louisiana, to be sure that it's real. And it was a clear signal of 2 black holes merging. One was 29 solar masses, one was 36 solar masses. So these are stellar mass black holes. We're talking about 10 to the 9th solar mass black holes. There's a big difference, and I'm going to skip this and talk about how you might measure the really big black holes. And it's by looking at arrays of pulsars, rotating neutron stars on the sky, and asking how the Doppler shifts of their signals change as a gravitational wave goes by. So these are millisecond pulsars. You can measure their frequency very well. And these are the telescopes, some of the telescopes, radio telescopes that are involved. You need a big array of them to be able to convince yourself that you're seeing something that spans the whole Earth rather than just some local phenomenon.
What's the frequency of these gravitational waves that you observe?
Nanohertz.
Nanohertz.
Yes.
Okay.
You have to be patient when you do these measurements.
Period. Sorry.
No.
10 to the 9 seconds.
Yeah. There are 10 to the 7 seconds in a year, so pi times 10 to the 7 seconds in a year. Another useful number to remember. Okay, but anyway, you know, a lot of people are now very spun up about the possibility of these radio antennae being used together, looking at pulsars, known pulsars, to measure the gravitational waves from the kinds of black holes that we've been observing. I'm going to skip the whole next part, and because you asked such good questions, I couldn't resist answering them. So, I'm going to talk just for a few minutes about why adaptive optics is needed to image the living human retina, so with emphasis on people, real people. I've had my eye imaged with adaptive optics. So here's Claire's poor attempt to draw the eye. This is meant to be your eyeball, the white. This whole thing represents the white of your eye, and in the middle you have your pupil surrounded by this colored thing that has brown or green or blue or whatever. And there's a lens in here. When your pupil is small, for example, if you're looking at a bright light, your pupil closes down, and you're not looking through the edge of the lens, you're looking through the middle of the lens. It turns out that the lens is not perfectly attached to the rest of your eyeball. And the cornea isn't either. So there are optical distortions. And at night, for example, when your pupil opens wide, or when you go to the eye doctor and he puts those horrible drops in your eyes that make your pupil big, you're literally looking through the distorted region of your lens and cornea. And you may have noticed, how many have noticed that at night sometimes you see flares around streetlights or halos or things like that? The same thing happens if a researcher or your doctor is trying to image the retina very clearly. You just reverse the sign of the light, and they can't see as clearly as they should in order to image individual cells in the retina. So here's an illustration of that put together by Austin Rurda at Berkeley. These are all the images of a point source, one point source. This is the ideal image that you would get through a 1 millimeter pupil, and then as the pupil gets wider and wider, remember the diffraction limit is lambda over d. As d gets bigger, the angular size of this image of a point source should get smaller. So if the doctor gives you these drops and your pupil opens up wide, she should be able to see much more clearly the cells in your retina. This is what happens instead. As your pupil opens up, you're uncovering these optical aberrations and seeing worse and worse instead of better and better. And that's not good, so adaptive optics is basically fixing that and getting you back to what you should see through a large pupil. So this was a very early adaptive optics system for the eye. I assure you they're vastly smaller and more compact now. They have to be because they're in clinics. But just to show you, there's a deformable mirror very much like the ones that we used in the early days of astronomy. There's a wavefront sensor that measures the wavefront. There's a science camera, and not shown here is there's a laser diode that sends a laser guide star-like dot onto the blind spot in your eye, and that's what's used to measure the distortions. So it's actually rather analogous to what we do in astronomy. Yeah, it makes you squirm if you think about it too hard.
Variation is not optical.
Well, it turns out that when you blink, you have a little tear layer that's out over your eye, and as it evaporates between one blink and the next, it changes with time. Also, when your eye focuses, it does it in a little servo. It's always jiggling around a little bit. So it changes. They typically run these at 30 hertz, so that's good enough. So without adaptive optics, here's an image of the retina. With adaptive optics, you're seeing individual cone photoreceptors, the color-sensitive cells on your retina. This dark line is the shadow of a blood vessel. It turns out the eye is made backwards. The blood vessels are in front The nerve fiber layer is in front, and they're both the nerve fiber layer is transparent, but the blood vessels cast shadows on the retina, so you're seeing the shadow here. And you can use optical coherence tomography in this case to actually make a section, 3D section of the eye. So this part of the eye is here, and you can see here's the nerve fiber layer. Blood vessels are in here, and you can actually study the shape of the retina, which turns out is an indicator of retinal disease. You can see holes, for example, in the retina by looking at it in a cross-section. Semi-finally, you can study color vision. So by shining different color light on the photodetectors in the retina, the cones, you can tell which cone is sensitive to blue light and which one to green light and which one to red light. These are two people who have perfectly normal color vision, indistinguishable from each other if you give them the standard tests that we all take. But notice the completely different cone patterns. This one has many more red cones than green. This one has about equal number. This one, they're pretty evenly distributed. This one, they're all in blobs, a blob here, a blob here. And yet these people both have completely normal color vision. I think this is absolutely remarkable. If this person looks at a white wall, they don't see blobs, they see smooth white wall. So there's a lot of processing going on in here to take these photo signals that your retina sees and make sense of them in the world. Finally, if you look closely, you can see little blood cells going through the blood vessels. So this was originally a stunt. It's blood cells moving through the capillaries. It turns out if you can measure how fast they're going and how many there are, you can get indications of the health of these capillaries, and many eye diseases start with problems in the capillaries. A diabetic eye has problems with the capillaries. And I don't know if this will ever be mass produced, because this first experiment was one graduate student counting blood cells. You know, there goes Harriet, there goes Margaret, there goes Joseph. But if we can automate this, and we have already stabilized, the community has already stabilized these images, it might be a dynamic way to look at the health of the eye. Thank you.
Time for one or two more questions?
Visible light, you teach us
Yeah.
visible light is coming. What are the obstacles for AO?
Yeah, so you need many more degrees of freedom in your measurement and in your actuators on your deformable mirror. And the reason for that is that, I'll go back to this. What matters in determining the size of the patch over which you're going to do the measurement, you divide your pupil into many little patches. How big do the patches have to be? They have to be small enough that the phase is coherent within a patch. Otherwise, you're going to be measuring some random quantity. And as you go to longer and longer wavelengths, you can use larger and larger patches, because these wrinkles will be a smaller and smaller fraction of the wavelength. So the atmospheric coherence length in the near infrared is maybe half a meter, whereas at 500 microns, 500 nanometers rather, it might be 5 centimeters. And that's because of the statistics of atmospheric turbulence. So if you need an actuator every little patch, then you're going to need more and more actuators if you go to shorter and shorter wavelengths. So typically, for these new 20 to 40 meter telescopes, they're talking about 5,000 to 10,000 actuators. And it's doable with today's technology, but it's expensive, and the computing is challenging, and the sensing is challenging, and so forth. It just gets a little harder.
Okay, so let's discuss some more
Yep.
over wine and cheese on the 6th floor, and let's thank Claire again.